Okay, I hope I'm audible. So, this is a TS session for the course Introduction to Astrophysical Fluids, and this TS session is going to take place every week on Tuesday, same time, 7 to 9. And so, in this TS session, we would basically discuss whatever material has been covered in this week. This is week 3 and we'll cover the materials of week 3 and we'll discuss if you have any questions or doubts or clarifications or any part from the lecture you want to revisit. We can go through that as well. So, let's take a minute to see if you have any questions, anything about the course or any lectures, any concepts from the previous weeks or this week as well. Okay, if not, so my name is Rohan and I will be the TA for this course. I am a PhD scholar in IISc Bangalore. So I work on accretion disks around black holes, which are basically fluid or plasma, to be more precise, which are basically dragged into the black hole as the black hole eats up a nearby star or any other object. So, in astrophysics, there are uh, many objects where we can apply the concept of fluids, and we'll get into that as we progress through the course. So, right now, we are in the stage where uh, we are just learning about the basic fluid equations, and then we'll see how we can apply them to astrophysical systems later on in the course. Okay, so there is a question. Um, Ramanan is asking, could you explain a bit about the momentum flux density tensor? We were asked a question on this in assignment 2. Okay. Uh, what do you want to know about the flux density tensor? Let me see what's the question. Do you have a question number for assignment 2? Okay, I guess it's question number 7 as far as I can see from here. Okay. Yeah, so I think I have it somewhere here. Okay. Yeah, I will explain it in this slide itself. Okay. I'll explain it. Any other questions? Okay, if not, then we can start with a recap. And when I'll be discussing this uh, first order moment equation, that will answer your question about the flux density tensor. Okay. So, anyways, so if you remember from the first week, we started with Boltzmann equation, which in a sense describes how ensemble of particles behave in a phase space. So F is the uh, uh, density, the probability density in the phase space of a particle. So basically, it is a function of uh, position, velocity, and time. And this is the equation which describes how the probability density of particles will evolve in time. Right? And this collision integral was given by this, and this was also derived in week one's lecture. Now, this is the fundamental equation uh, which we obtained by uh, basically without using any assumption, right? And from there, we saw later that we can derive all the fluid equations which describe uh, the flow of fluids. So basically, now we also studied another important distribution, which is called the Maxwell's distribution, and this is given by this term. So how we derived at this Maxwell distribution, we assumed. So we basically took the condition, we enforced the condition that uh, the system is in equilibrium. And now we ask the question that how should the distribution function or f look like if the system, if we have a system which is in thermal equilibrium. So by thermal equilibrium, I mean that all the energies are evenly distributed among the particles, right? So if any system which is in thermal equilibrium will have a distribution which is given by the Maxwell's distribution, right? So for example, what this equation is telling you is that what is the probability that a particle with velocity v, uh, yeah, so basically what is the uh, probability that any particle in the distribution will have a velocity v, and that probability is given by this function, right? So if you see, if you have very high velocities, right, and then the particle will have the probability of that particle to have such high velocity will be very low. So if you remember the plot of this Maxwell's distribution, it seems like a Gaussian, like a skewed Gaussian, with the long tail on the right hand side, right? So that means that you don't have many particles towards the extremes, not many particles with very high velocities, and neither many particles with very low velocities. You will have most of the particles will occupy a region which has velocities somewhere in between, right? Okay. So, yeah. Now, from the Boltzmann equation, we took different moments and we arrived at the continuity equation, which is the zeroth order moment. And from there, we took the first order moment to get this equation, which is the momentum equation. And now, now you see this momentum equation, this del d of nv plus del dot nv tensor product v equals to uh, divergence of this pressure tensor. Okay, this is the pressure tensor divided by m plus n a, which is the acceleration of any external forces, right? So this is simple Newton's law. And now, what is the momentum flux density tensor? So if you just uh, take this term, the del dot p term, to the left hand side, and combine it with this term, so this will become del dot n v cross v plus pressure tensor by m. So this whole thing, v cross v plus pressure tensor. So this is actually the momentum flux density tensor term, right? And why is it called momentum flux density? So I will come to this also later on, but now since you asked the question, let me just clarify it here. So if you remember in the week one course, so when we are talking about the conservative form of equation, so what do these conservative form have? So for example, let's take the continuity equation. So del rho del t. So basically, it talks about how the density changes with time. So that is equal to the flux that is going in or out of that volume, right? And that flux is defined as del dot rho v. So this is the flux term, right? Similarly, if you look at this first order moment equation, so it says that the change in the uh, momentum. So this term is basically the momentum, right? So n times v. So with the if you just multiply it with mass, this will become the momentum mv. So the change in momentum is equal to the uh, flux of momentum that is going in or out of that volume, right? So that's why this term is called the uh, momentum flux, right? Uh, I hope that is clear. Okay. Okay. So again, these equations are derived in week two lectures. So yeah. So as I was saying, these lectures will be recorded and they will be available on my YouTube channel. So I'll later on, so that later on you can uh, go out and see those lectures if you feel like recalling something or anything. So I'll just share the link of my channel so that you can get access to all the lectures over there. So I'll just quickly share the link on chat, maybe. Okay. So I've shared the link. So you can find all the week's lectures starting from week one and even future lectures over there on YouTube. Say, okay. So if you want to see a derivation of these equations, you can go back and look at the week two's lectures. So I think zeroth and first order moment derivation was done by the professor in his lectures, but the second order moment derivation was not done in the lectures. So that also I have done in week two lectures. So if you want a derivation, you can go back and look it up here. So I just explain what this equation means. So if you take the second order moment, so this will give you an energy equation. So for example, the first order moment was giving you the momentum equation. The second order moment will give you the energy equation. So this epsilon is the internal energy of the fluid, right? And so the change in internal energy of the fluid is dependent on this flux of internal energy, and there is some additional term which is basically, so this Q term is the heat flux. So if you are having any external heat uh, flowing into the fluid or not, so that will also determine how the internal energy of the fluid changes. So this Q is the heat flux, and this P is the pressure tensor as always, and this lambda is given like this, right? So this is the P contracted with lambda, right? So yeah, any questions on this? Yeah, sure. Right, right, right. Okay. Yeah. So yeah, it's a good question. So basically, you see what we are trying to do. So we are trying to look at a volume in phase space, right? So your phase space volume is D3R, D3U. Okay. So because your phase space is a space of R versus U, it's not a position space, right? So it's a R is on the x-axis or whatever, and U on the other axis. Now, if you consider infinitesimal volume in the phase space, you can think of it like D3R, D3U. So that is your volume. Now, what you want to do is, now there are collisions happening between the particles, right? And you have some particles uh, within that volume, which has velocities between U and U plus DU and position R and R plus DR. Now, since there are collisions happening between particles, so what will happen is the phase space will evolve. So if there are collisions inside the volume, so particles will have velocities between u and u plus du, and in the next instant, after the collision, the particles might go out of that volume, and they will have some different uh, velocities. They will go into a different phase volume, volume in phase space. Right. And similarly, so that is basically your C out. So C out is you're calculating how many particles are uh, going from inside the volume to outside. And C in, on the other hand, you can also think of it that uh, since there are collision happening, so it could also happen that particles from outside that volume could also come in after the collision, right? So that is basically your C in. So in C in, you are considering that the initial velocity of the particle was u1, right? And so after collision, u1 will go to u. After the collision, the velocity of the particle will become u, and it will go inside the phase space volume. So basically, that's why you are basically adding the particles which are coming in and subtracting out which are going out, right? And you are integrating over all those velocities which are possible, right? So all those velocities which will give you a velocity so that the such that the final velocity comes within the volume. Does that answer your question? Right. So if you are calculating C out, no, if you are calculating C out, then what you are calculating that all the velocities which are inside the volume that is going out. So inside the volume, what are the possible velocities? The possible velocities are all u's, right? Because inside the volume, the uh, particles can have velocities between u and u plus du. So if you're calculating C out, that's why you are integrating over du. If you're calculating C in, you're integrating over du1. I mean, it depends. Like U1, U1 are just the names, but you can consider that the volume inside can have velocities U1. Like whatever, it depends on your convention. But the idea is that when you're calculating the C out, you have to consider all the velocities, integrate over all the velocities which that volume can have, right? And when you're calculating C in, you have to consider all the velocities which, you know, the outside the volume. Right. Okay. So yeah, I guess that is clear. Any other questions? Okay. If not, let's move on to this week's material. So let's see. Okay. So now from these moment equations, we are going to simplify this moment equation into a set of uh, simpler equations, so to say. And why I say simpler, it's not because this equation has, a lot of terms or something like that. But I say simpler because if you see here, I mean, let's count the number of variables this equation has. So these are three equations. Whereas, how many number of variables do you have? So your unknowns are basically this n is unknown. Uh, that's one. U vector is unknown. That's three. So basically, okay, U and V are the same thing. I should have made the same convention. But anyways, so let's consider that V velocity has three directions: Vx, Vy, Vz, and those three are unknown. So 1 plus 3, 4. What else? P. P is a symmetric tensor, uh, and that will have six variables, six unknowns. So 1 plus 3 plus 6, that is 10. What else? So 10, then internal energy, epsilon is unknown, 11, and then Q. So Q again is a heat flux vector which will have three directions, Qx, Qy, Qz, and you have total 14 unknowns, whereas you have three equations, right? So it's an unsolvable system, basically, right? So how to reduce it to something which we can solve, right? So if you see these definitions, right? So if you see, for example, Q and okay, Pij. Uh, okay, I didn't mention the Pij here, but Pij is basically uh, this pressure tensor is basically u minus v uh, whole square, basically. Yeah, ui minus vi times uj minus vj, and average of that. So okay, I will just explain qualitatively first, and then if you don't get it, maybe I can write it down in my notebook and then explain it to you. But let me first explain qualitatively what is happening. So let's say, let's consider, okay, so the zeroth order equation. So if you just multiply this equation with m, you can get this first equation, right? So m times m, n is rho. So del rho del t is del dot rho v equals to 0. So that is just the continuity equation. We have done this a lot of times. Okay. So this is pretty simple. Now, how about the second equation? So how can we simplify this equation, right? Simplify this equation into this equation. So the main thing is this term, this del dot pressure tensor. This pressure tensor will have six unknowns, right? So how can we reduce that six unknowns to just one unknown, which is just P? So the idea is that so this P is average of Ui minus Vi, as I said, times Uj minus Vj, right? So let's say if you and how can we calculate the average? So I think all of you know that the average of any quantity is basically that quantity times this Maxwell's distribution F and integrated over all the values, right? So if you integrate, let's say Pij, so where I naught equals to j, then what you will have an odd function, right? And you have integrated over all the velocities, right? From minus infinity to infinity. And we know that for an odd function integrated from minus infinity to infinity, it will give you 0. So all the cross terms, by cross terms I mean Pij where I naught equals to j, this pressure tensor will become uh, 0, right? Only for the diagonal terms. By diagonal terms, I mean when pi, so by diagonal terms, I mean I equals to j, right? So only the diagonal terms will survive because that will become an even function. Because as I said, this will be ui minus vi, uj minus vj. So if I equals to j, then it will be ui minus uj whole square. So that will become an even function. And for the even function, this term will be non-zero, and that term is basically taken to be this small p, which is called just the pressure, right? And then this term will become equivalent to this term, which is the Euler's equation. So is it understandable, or should I write down something? Not really. I said it will become an odd function because okay, let me write it down. I think I missed the P here. So Pij. Why is it not visible? It is visible. Let me just write the equation over. So okay. Okay. So Pij would be something like this: Vi minus Ui times Vj minus Uj, and the average of this, right? So as I said, when you are doing average of some quantity, you have to multiply it with the Maxwell's distribution Fv and integrate over all u's. Now this i's and j's are basically the directions. So this could be x direction, y direction, or z direction. So if let's say I is not equals to j, so let's say if you are calculating xy, so I is not equals to j, so that then what will happen? Vx minus ux times vy minus uy. So, by the way, so this V's are the velocities and U's are the mean velocity. So this is an average velocity in that particular direction. So Vx minus Ux times Vy minus Uy. So this is an odd function in X, right? So if you integrate over all the velocities, all the Ux, so this will be an odd function in X and odd function in Y as well, right? So that's why this will become 0 because you are integrating from minus infinity to plus infinity. That's clear, right? Okay. Okay, so now let's go back. This okay. But if you see that, Okay, let me write it again. So Pij is equals to Ui minus, sorry, Vi minus Ui times Vj minus Uj. So if you, but on the other hand, if I equals to j, so this term will become, so Pii will become Vi minus Ui whole square average. So this will become even now because of the square term, right? So then it won't be zero. And that term is basically the pressure term. Now, yeah, let's look at the second order moment equation similarly. So similarly, mm, again, you can contract the P term in a similar way. You will only have P left. And along with that, so if you see that P survives only if I equals to J, right? So for all I not equals to J, this term will go to zero. But what for I equals to I term? So I equals to J terms. So I equals to J terms, this lambda vector, if you see from here, this will turn out to be del Vi del Xi plus del Vj del Xj. So this will be basically just a divergence, right? Del dot V. Okay. So del dot V is, I think you know, del Vi del Xi summation. Right? So similarly, okay. So that's why. So you see this term becomes like this del dot V. So this is coming from uh, this this term. Now what about this Q term, this Q vector? So if you see from the definition of Q here, again, so this is an even term u minus V mod whole square. So let's leave it out. But on the other hand, if you there is an additional multiplying factor of u minus V, which will make this q function to be odd, to be an odd function, right? So again, this will become, uh, zero in all the cases, right? Okay. Okay. Now, so from these three equations, we got these three corresponding equations, right? And now let's check how many variables we have. So we have this row one variable. V vector will have three variables, so four. P is another variable, five. And we have epsilon, six variables. Right? Yeah, that should be it. So six variables, and how many equations we have? So we have, this is one equation. This, you see, is a vector equation. So this is not a single equation. So you can decompose this equation into three different equations. So for example, this is V vector. So you can have similar equations for del Vx, del Vy, del Vz, like that. So you have 1 plus 3, 4 plus 5 equations, right? So epsilon is a scalar, which is the internal energy. So you have uh, six equations. Okay. So yeah. Now six equations, and you have, sorry, I miscounted, right? Three, four, five, five equations, right? So 1 plus 3 plus 1. So five equations, but six variables. So you have one extra variable. So now what to do is that we need to impose another equation, which is called the equation of state. Right? Now, what does equation of state say? Equation of state say that, so for example, for an if you know that rho is m times n, and for an ideal fluid you have P equals to nkt, right? And epsilon, the internal energy, is 3 by 2 kT by m. So you will, for any fluid, even if it's not ideal, you can in general obtain an equation which relates the pressure in terms of density and internal energy. So if you obtain this equation, then you have a complete set of six equations and six variables, right? And this is actually an active area of research for many uh, uh, people who work in neutron stars, for example. So neutron stars are these highly dense stars, and right till still now, people don't know what is this relation, what is this equation of state that follows for the material that is inside the neutron star, because they are in a very high pressure and high temperature environment, which cannot be reproduced in labs in Earth, right? So they are only found in those environments. Those conditions can be found only in very extreme uh, environments, and this is something which people model for those systems, and they try to solve all these equations by using a model equation of state, and they try to see which model will give them the most uh, best estimate of all the quantities that we observe, and then they try to guess the equation of state for such systems. Okay, so any questions on this slide? Okay, if not, let's move on. Okay, now just a little bit aside on Lagrangian versus the Eulerian approach. So let's say you have a fluid particle which is uh, moving. So there are two ways to look at it. So one way could be, so inside a, let's say, a fluid, there are a lot of particles which are moving. Now, one way you can determine the path is by following the particle itself. So you see, you follow the particle, and wherever the particle goes, you go along that trajectory and you trace out that path of the particle. And from that path, you can determine what is the velocity and what is the, uh, you know, uh, all the other properties of the fluid, right? The other thing that you can do is you can focus on a single patch of fluid, right? So you can say that, okay, I will focus on only this patch, and doesn't matter what particle is coming in through that patch or going out through that patch, or whatever is happening through in that patch. I don't care. I'm just focusing on this patch, and I'm calculating whatever the all the particles that are going through that patch. I'm calculating their velocities. But remember that when you are focusing on that patch, the particles that are coming in and going out will be changing every moment. You're not focusing on a particular particle. You're focusing on a particular patch. The particles inside that patch will keep on changing with time, right? So, well, Lagrangian method is the first method where you follow the particle, right? And the Eulerian method is the second method where you follow the patch. And it turns out that there is a relation between those two approaches, the Lagrangian and the Eulerian approach. And but the question is, why these two approaches? Why do we need to consider these two approaches? So it's easy to think that so when you follow up particle, it's easy to calculate the forces on the particle. You would know Newton's laws, right? So you can apply Newton's laws on that particle and you calculate the forces that are acting on that particle, and then you can just uh, have the Newton's laws, and from there you can have the uh, evolution equations of the fluid, right? But you see, the Eulerian approach, in order to know uh, in real life situations, you're not following the particle. You are basically trying to see what is happening in the fluid at that particular position, right? uh, I mean, a particle could get out of the system, right? So you're not going to follow the particle out of the system. So what you will do is you focus on a patch of fluid, right? And that's why the Eulerian approach is important. And um, yeah, and most equations of fluid are basically written in this Eulerian approach only, right? Now, we do have two different approaches, but there is a relation between those two approaches. So, as I said, in the Lagrangian approach, a flow variable could be expressed in terms of FAT. So A is the initial position of the particle. So this R0 is A. So if the particle starts from here and you follow the particle, so it will have different position at different time. R is a function of time. And this particle will have different flow variables. This will have a U at this particular instant, a different U at different instant, and so on. But any flow variable can be expressed in terms of this as a function of A and T, right? If you know where the particle started from and you know at what time you want the variable, you can calculate it. And any position vector at any random time, so let's say at any given time Rt, this position vector will be a function of Ra, comma T, right? And in Eulerian description, as I said, one concentrates on what happened at a spatial point, which is R prime, comma T prime. So X, Y, Z prime and T prime. So you are only focused on this point. You are not following the particle. Particle might be at a different point altogether at different instant, but you're only focusing on this point. Right? So okay, let's see what the relation is between these two. You know, uh, these two approaches, right? So let me go back to my notebook again. It's a short derivation, but I think we should get to it before we move forward. Okay, so fine. Okay, so in the Eulerian approach, sorry, in the Lagrangian approach, as I said, you can express any flow variables in terms of this, right? Now, so this is the Lagrangian approach, and this is the Eulerian approach. Okay, so if you want to have the same flow function at a particular time, if you are imposing this condition, so let's say a particle is, you know, so let's say this, if you follow the Lagrangian approach, you follow the particle, and this particle is at this point at this particular time t, right? And this is the position of the particle r comma t at this point. And in the Eulerian approach, this point is given as r prime comma t prime. So if the particle is at this point, so the flow function should be same uh, in both Eulerian and Lagrangian approach, right? Now, if we do del f del t of the Lagrangian approach, we get del f del t prime del t plus del f del r prime times del r prime del r del t. Right? Now, t prime and t are just choice of units, and this will become 1. So if you consider t equals to t prime, so this is just a choice of units in your Eulerian frame and your Lagrangian frame, right? Similarly, r and r prime will become 1. This is also a choice of units in your Lagrangian and Eulerian frame. So what you are left with is del f del t prime plus del r del t is v dot del f del r prime. So from here you can get uh, del f del t in the Lagrangian frame is equals to del f del t in the Eulerian frame plus v dot del f del r. So del f del r in general, we can write it as v dot delta f. Okay. So this is in the Eulerian frame. So that's the relation between Lagrangian and the Eulerian frame. So yeah, and also in just for convention, so this del f del t in the Lagrangian frame is generally represented as a total derivative. So this is d dt of any variable, let's say f, is equals to del f del t plus v dot delta f. So this is generally written like this. So for example, I'll just give one example. For example, okay, so let's say d rho dt is equals to, let's say 0. Okay. This is not 0, but let's assume for an incompressible flow, if this is 0, so then the equivalent equation would be del rho del t plus v dot del rho equals to 0. Okay. Now, can you tell like what under which condition this equation is valid? So the original continuity equation is del rho del t plus del dot rho v equals to 0. So this can be broken into del rho del t plus rho del dot v plus v dot del rho equals to 0. Right? So only if del dot v is 0, then this will reduce to this. Anyway, this was just an example. But yeah. So generally what I am trying to say is that d dt is equals to del del t plus v dot del. Okay. So yeah, in more concise form, let's just write it here. D dt equals to del del t plus v dot del. Okay. So this is the takeaway from this slide. Okay. Any questions? Okay. Let's then form. Okay. So yeah. Okay. So now we have simplified these four equations. Okay. Now we'll learn some properties of these four equations. So this is the momentum equation, the second equation that we have over there. Now this is an identity. Now let's see if we can simplify this equation using this identity. So you see this term v dot del v. So this identity is v dot del v equals to del of v square by 2 minus V cross omega, where omega is del cross V. And this omega is called the vorticity. So if you see, like physically, what does it mean? It means that, so when you take curl of any vector, so it means that how much of the, uh, so for example, so you have heard about electric fields and magnetic fields, right? So for example, how does the electric field of a single charge looks like? It points outward um, from the charge, right? If we have a single isolated charge, so it goes outward. So that means it goes straight out. So it doesn't have any curl. On the other hand, if you have uh, a wire with current flowing through it, the magnetic field around the wire would follow a spiral uh, shape. It will have a spiral shape. So those magnetic fields have a non-zero curl associated with it. So that's how at least I try to visualize curl of any vector fields. Right? So I think electric fields and magnetic fields are a good way to think about it. So similarly, for example, so if you have the velocity vector in such a way that it curls around, right? So for example, uh, let's say a tornado or something, right? So the fluid will go around in a circular pattern. So they will have non-zero vorticity, right? So yeah, so using this identity, we can go from this equation to this equation, right? So for example, this will go into decompose into del v square by 2, and you have a minus v cross omega, so which will go over here on the other side, v cross omega, and plus g as is. Now, you see, we have a del v square by 2, and we have this del p by rho. So there is one condition under which we can bring this whole thing into the gradient term, right? Because you see here, the gradient is only on p, it's not on p by whole p by rho inside the gradient. So the gradient is v square. So there is only one condition under which I can do this. So that is called the incompressibility condition, which means that the del rho is basically zero. And what does it mean? It means that the gradient of rho uh, is zero. So that is, over space, the density doesn't vary much. Okay, so the density is uniform. So that's the incompressibility condition. So under that condition, uh, you see that since del rho is zero, I can take the whole thing inside the gradient term, and then finally we can, you know, combine the v square by 2 term with the p by rho term, and you get this equation from this equation. Okay. Now, from here, we will derive another equation which is called the vorticity equation. So, okay. So now, if you consider this term, this equation, and you take the curl of this equation on both sides, right? So, curl of del v del t is curl of v will become omega. So, this will become del omega del t. And there is a theorem which states that curl of gradient is zero. So del cross gradient of any term, any value would be zero always, doesn't matter. So this term will then become zero because you're taking curl of a gradient of something, and this will become zero. Then curl of v cross omega will become curl of v cross omega here, and curl of g is again zero. So if you consider just mm, well, as I was giving the example of a electric field, so similarly, the gravitational field, the curl of it will also be zero because it is completely radial, right? So there is no curl in there. Okay. So right now, this extra term is the term that is coming from this term. So the first row is when we don't have any incompressibility condition. The second row, the second equation is when we have the incompressibility condition. So if you have so let's look at the second equation first, then I will derive the first equation. The second equation directly comes from here, I guess. So that I guess you can see. So del dot V is omega, and this del cross V is omega, and this term will go to zero. You have del cross V cross omega, this will again go to zero. So this is the second equation that directly comes from here. Now for the first equation, so okay, let's derive this equation. I think that will be better. So this is your Euler equation, right? Now, what was the identity? The identity was V dot del V equals to del of V square by 2 uh, minus V cross omega. Right. Okay. Now, let's assume that we do not consider any incompressibility or any other condition. So then if I just do del cross of this equation, right? So the first term will again become del cross del omega del t, and del this term will become del cross del of v square by 2 minus del cross v cross omega, and this will become del cross del p by rho, and this is del cross t. Now, as I said, del cross t is 0, and curl of gradient is again 0, so this two term will vanish. So we have del omega del t equals to del cross v cross omega, and this is del cross del p by rho. So here we just apply simple, chain rule. So like ddx of u by v is v du dx minus u dv dx divided by v square, right? So simple like that, we can apply over here. So here v is rho. So you have rho square. So v du dx. So instead of d, we'll have del cross because we are applying curl. So del cross del p plus del p, or sorry, minus del p cross del rho. Right? So as I said, curl of gradient is 0. So this del cross del p would become 0 again, and you are left with this term, del p cross del rho. Okay. So then this equation del omega del t will become del cross v cross omega plus del p cross del rho divided by rho square. Right. So that's how you get this equation. Okay. Right. So this is the first row is the original equation without any assumption. But if you assume that the fluid is incompressible, then you get this equation. So there is another uh, condition which will also cancel out this term apart from incompressibility. So as I said, that incompressibility basically means del rho is 0, right? Another condition is barotropic condition. So which is basically this thing, that pressure is a function of rho, right? So then also this term will become 0. I will come to this why this becomes 0 if we assume the barotropic condition. But let's uh, look at the okay. Let's see why it becomes zero first. So okay, so if let's say your pressure is a function of rho, so then what will happen? So del P will be F dash rho del rho, right? So that is del P. Now, if you have del rho cross del P, this term will become del rho cross F dash rho del rho, right? So F dash rho is just some function, right? You can just take it out and you have del rho cross del rho. Now, what is del rho cross del rho? So del rho is basically a vector, right? And any vector cross the same vector is basically zero because the angle between them is zero and sine zero is zero. So A cross A is A square sine theta, the angle between them. Well, in this case, theta would be zero. So sine zero is zero and this term will become zero. Right? Okay. So yeah, that was uh, trivial, but should be pointed out. So if pressure is a function of rho only, so then this term will be zero. So that's why for barotropy condition, this term cancels and you are reduced to this equation. Similarly, for incompressible flow, as I said, del rho is zero, so that is even easier to visualize that this term will become zero and we will get this. Now, let's see, we have another even simpler cases for incompressible fluids, right? So for incompressible fluids, we can get to other conditions which also satisfies. For example, if del rho is equals to zero, so let's see what are the consequences of del rho equals to zero. So here it says that if del rho equals to zero, so then del dot V should also be equals to zero. And this del square P is equals to this thing. So what this means is that the pressure is not an independent quantity. So if you remember when we are saying that we have six variables, six equations, so basically you will have one less variable because the pressure could be, uh, you know, expressed completely in terms of the velocity, right? So that is another important thing that we get for incompressible fluids. So let's see how these two conditions, how we can get to these conditions. So again, let me enter. Let's open a new. So the first condition basically comes from the continuity equation. Del rho del t plus del dot rho v equals to 0, right? So this will become, as I said, del rho del t plus rho del dot v. By the way, I guess you can understand which are vectors, but I should give a arrow sign over them. Anyways, so del rho del dot v plus p dot del rho equals to 0. Right? Now, uh, well, so all these things we are studying under steady state. So by steady state, I mean that the the system has evolved enough that it is not changing with time. So for example, whenever I say steady state, what you should think about is del t equals to 0. The time derivative is 0 because the system has reached equilibrium state. Well, equilibrium is not the right word, but steady state, it means that the system will not evolve anymore with time. So del t is 0. So this term will go to 0. And from the incompressibility condition, you can see del rho is equals to 0. So this term will also become 0. So we are just reduced to del dot v equals to 0. Right? So for incompressibility fluids, so this is the second condition. So the first condition is, let me write down, del rho equals to 0. Second condition is del dot v equals to 0. Another condition we can derive for incompressible fluids from the Euler's equation. So we have del v del t plus v dot del v equals to minus del p by rho plus g. So as I said, steady state, this will go to 0, right? And also let's assume that there is no external forces acting on it, because if there are external forces, the system cannot be in steady state, right? You can Newton's laws, basically. The system will evolve with time. So external forces are also 0. So now you can see that you have a simple relation between P and V, right? So del P equals to rho times V dot del V, right? And if you take, uh, basically, do a del dot on both sides, right? Take divergence of both sides. So del dot del P is del square P, and you have del dot this thing, rho into V dot del P. Now, again, if you apply chain rule over here, you take del rho once, so this will go reduce to V dot del V times del rho plus rho times del dot V dot del V. Now, again, from incompressibility condition, del rho will become 0. So del square P will be this thing. So this is another condition that we have for incompressible fluids. And this just states that, the pressure can be expressed in terms of velocity. So instead of, you know, uh, 6 variables, we'll have 5 variables in total. And what does this do? As a consequence, the energy equation will become decoupled. So for example, let me show it over here. Okay. So here you see that, okay, so this P can be expressed in terms of V, velocity. So if you consider only these two equations, so how many variables do you have? You have rho and 3 velocities. So you have 4 variables and you have 4 equations. So these 4 equations can be solved independently. And the energy equation again can be solved independently, right? So yeah, so that is the consequence of uh, incompressible fluids. The energy equation is decoupled. Any questions on up to this? Okay. Question? You just apply chain rule. Okay, so now we will do one theorem which is called the vorticity theorem. So we already looked at the definition of vorticity, and we also derived this equation for incompressible flows, right, which is the vorticity equation. Now there is something called the Kelvin circulation theorem, right? And what it states that, uh, okay, let me define circulation first. So circulation is defined by this symbol gamma, and you have v dot dl. So if you know Stokes law, okay, so this v dot dl, so let me explain this term, what this means physically first, and then maybe I can connect it to vorticity. So v dot dl integrated over a closed surface. So this symbol means a closed integral. So if you have some fluid, let's say, if you look at this picture and you, let's say, have a fluid which is moving like this, and you consider an imaginary, uh, you know, loop, right? Like this shown over here. And if you integrate this quantity, let's say here it is v vector, integrate v over this loop. So this is what is called a closed integral. And the circulation theorem says that this integration or this uh, term gamma do not change with time, right? So if you uh, okay, so if you consider a closed curve at this instant of time, let's say t1, and then if you consider uh, at a later time t2 another closed curve which contains the same fluid elements, right? So then you can say that uh, that d gamma dt is 0. So that means that the gamma do not change with time if you consider the same fluid elements. So this is the physical meaning of the statement. Okay. So we'll do one example after this. Maybe then it will become clear. But let's just have a one line proof of this uh, of this uh, of this theorem, right? Okay, before the proof, so let's see that these two statements are equivalent. So if you see this statement, gamma is okay. So del gamma del t, not these two statements. That's the definition of gamma. Del gamma del t equals to 0 is equivalent to saying this thing, del t of omega ds equals to 0. So how is this coming from? So this is basically coming from the fact that uh, from Stokes theorem, basically. So if you know Stokes theorem says that del cross any vector, let's say A, del cross A, and if you have integrated over a surface, the surface integral of del cross A is equals to the A dot the um, A dot dl, where dl is the boundary of that surface. So that's how it comes from. So del cross phi is omega. So del cross phi dot ds will become integration of phi dot dl, right? So this is basically the gamma. Omega dot ds is gamma, right? And ddt of that thing is 0. So this another way of physically understanding this theorem is that within this surface, the vorticity will remain constant over time, right? So whatever vorticity you have in this surface at this instant of time, at any instant of time, it will remain constant, right? And the condition for this theorem to hold is that the forces that are acting on this system should be conservative, and the barotropic condition that we saw earlier. So why conservative, and what does conservative forces mean? So conservative forces basically mean that any force which can be expressed as a gradient of some potential. So for example, gravity is a conservative force. So it could be expressed as a gravitational potential. So you guys must have heard about gravitational potential, right? So any force which can be expressed as a function of some scalar potential, so that is a considered to be a conservative force. Okay. So yeah. Now just to give a short proof of this. So this proof just comes from the Euler's equation, right? So if you just do dl v dot d, so yeah. So how will you get this term? So this G can be expressed in terms of del phi, as I said, because it's a conservative force. So you have integration over del phi dot dl. So that will come from this term. And from this del p by rho term, you will get del p dot dl. which is basically dp by rho, circular integral, closed integral. And from this term, if you do dot dl, something like this. Okay. So it's a closed integral v dot d dt of dl. So which will reduce down to, so this d dt of dl will be dv, right? So this will be integration over v square, and integration of v square across a closed loop will become 0. So because yeah, any scalar function which is integrated over a loop will become 0, because you will have same values on the either side of the uh, starting and the end point, right? Similarly, dp by p will also become 0, and del psi dot dl will also become 0 across a closed loop, right? So then finally what you will get is the circulation is basically 0. So this is not actually d, uh, this is not actually del, this should be d, okay? This is not del, this is total derivative. So if you want, I can just also show this on the notebook. It's just a one line derivation. So if you consider the Euler's equation, so let's just quickly. So this Euler equation, I already have written it over here. So let's see. So del V del T plus V dot del V is d rho dt, right? So as I said, the Lagrangian versus the Eulerian. It's not showing, right? Okay. Yeah. So sorry, del V. So I'm writing this equation. So del, so this is d, okay. So that means it will consider, it will take care of both the terms, the first two terms. So this is del p by rho plus del phi, right? Now, okay. Now your gamma is given by v dot dl, circular integral. Okay. And if you do d gamma dt, this will be d dt of circular integral v dot dl. Okay. So just apply chain rule. So by applying chain rule, you will have self uh, dv dt dot dl plus v dot d dt of dl, right? This is what you will have. Now let me do it here maybe. Okay, so for the first term, let's write the first term dv dt dot dl. So I just use the Euler equation to get the dv dt, right? So this equation to write dv dt. So if you write dv dt using that, you will get del p by rho minus dot dl plus integration of del phi dot dl, right? Okay. So del p by rho dot dl will become dp by rho circular integral plus, and del phi dot dl will become d phi. Okay. So again, as I said, this two term will become zero if you do a closed loop integral. Okay. And as far as the second term is concerned, where you have v dot d dt of TL. So this will be integration of v dot dv, right? So this will become integration of v square, sorry, dv square, right? Integration of dv square by 2, I guess. Yeah. So dv square is v dv plus v dv, and that's why we have a by 2. And again, this will become 0 if you do a closed loop integral. Right? So closed loop integral of any scalar function is always 0. I didn't prove it, but basically just if I have to say it in single line, maybe I would just say it like this, that when you have integration over some function d phi from 1 to 2, it will be basically phi 2 minus phi 1 line integral, right? But if you have a closed loop integral, so that means it will be 1 to back to again 1. So this will become 1. So phi 1 minus phi 1, that should be equals to 0. Right? So yeah. So that's why these closed loop integrals will reduce to 0. Any questions on this? Okay, so okay, okay. Let's see the conservative form of fluid equations. So, what is a conservative form? So any quantity which is conserved, that means that it doesn't change with time, right? So d at dt is basically 0. And as we said that we already learned how to go from Lagrangian to the Eulerian approach, right? So this will reduce to this thing if you go to the Eulerian frame, right? So the conservation equations will look something like this, right? So yeah. Now, yeah, so this is true only for intensive variables like pressure, temperature. Okay. Uh, yeah. Okay. So to give an example of uh, how a conservative form looks like. So let's say that you have a fluid whose density is rho. If you integrate over the volume, rho dv, you'll get the mass. Now, no matter what happens, you are not adding mass into the system, or there is uh, no way that mass is leaving from the system. Like you are considering the whole system as a whole, then dm dt would be 0, right? So if you do dm dt, you will get d of integration rho dv by dt is 0, right? And similarly, this will be d rho dt dv equals to 0. Now, here you see what this physically mean is that what is the change of density uh, in time from this small volume dv, right? So here you are only considering the small volume dv. So although the total mass do not change, total mass of the system do not change, but let's say if you consider a small volume dv within that within the system, there could be some flow of fluid coming into the volume, and there could be flow of fluid going out of the volume, right? So the change of density is basically this integration over all the flux that is going out or in of the volume, right? So this is given by W, which is the flux of fluid going in or out of the volume. So this integral over del dot omega. And again, from the divergence theorem, we can say that del dot of integral over volume integral of del dot omega Okay, I think I missed a volume integral. So this is a del dot omega dv. Okay. So del rho del t is basically del dot rho v. This w is basically rho v over the volume dv. And according to divergence theorem, you can express it at w dot ds. So which is the surface of the uh, volume, and the change in density is basically how much flux is leaving through the surface of that small volume dv. So yeah, so the continuity equation is a good example of that. Now the question is, can we also represent the rest of the equations, uh, say the momentum equation, that is the Euler equation, and the energy equation in similar form? So basically so why do you want to express the equations in conservative form? Because from here you can easily understand from a physical point of view that the change in some quantity is equal to the flux of that quantity moving in and out of that volume, right? So here we can have a physical significance of what the flux means, right? So similarly, so this is the flux of density. So what should be the flux of momentum, rho v? So which is the momentum? And it turns out that this equation can be represented like this. So this is also directly can be seen from the, uh, you know, from the first moment equation that we saw earlier, right? So in absence of external force, so this is the external force term. So this will become zero, right? So then again, we can express this terms in terms of the conservative form. And this is basically the momentum flux, right? As I was saying earlier as well. So this is how we get to the momentum flux thing. Similarly, can we also do it for the energy flux, right? So okay, so let's derive this equation. This is a little bit more complicated than the momentum flux equation, but let's have a look at it. Okay, another condition that I have to mention in order to derive this equation is that you have to impose that the fluid is incompressible. And we know what incompressible means, right? It should follow these conditions. Okay. So, so let's have a look at this equation, the energy equation once. We'll use this equation, and along with that, we'll also use this Euler's equation to derive the uh, conservative form of the energy equation. So if you see that del dot V due to incompressibility condition, this will go to zero. So you will be left with this equals to zero. So let's see this thing. So del epsilon del T plus P dot del epsilon equals to zero, as we saw. And if I just write the momentum equation, del rho V, so this is del T plus P dot del V equals to minus del P. We are considering no external forces. Now what we'll do is we'll take this equation and we'll do a dot product with V. Right? So if you do a dot product with V, so this term will go inside. So so this will become del of rho V dot V. So V dot V is V square. Okay? Plus this will become rho times half V dot del V square. Right? So can you visualize this? Why this is v dot del v square? So if you can't, you just expand this thing. So so del v square is v del v. Okay, uh, v del v, and then you have a v dotted with it, right? So yeah, del v square is v del v plus v del v twice. So that's why you have a half factor over here, and then you can obtain this term. Okay. Anyway, so moving on. Uh, this is the second term, and the third term will be v dot del p. Okay. Now, as I said, due to incompressibility, this can be written as del dot pv. Why? Because if I write it as del dot pv, so this will become del p, v dot del p plus p del dot v. And this will become 0 because of incompressibility. So this is same. Okay. 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 So, okay, let's have a look at this equation only. And this equation, right? And what we should do is let's add it up. Okay. So we have del t of e plus rho v square. Let's do a half over here. This is just a half factor, uh, because this will have the physical significance of a kinetic energy, right? So rho v square, half rho v square is the kinetic energy. So I just explain the physical significance of the terms later on, but let me just write it down. So if you just add these two equations, so from the first term plus first term will give you this thing, right? Now you have v dot del terms, right? And inside the v dot del, you have epsilon plus p plus again half uh, rho v square. Okay. Let me check, is that right? Rho v. Okay. Okay. Let me see. V dot del. Yeah, I think that's right. Okay. Yeah. So epsilon plus p plus half rho v square. Now, as I said, due to incompressibility, del dot v is 0. So we can take this velocity term inside. So we will have del dot this thing half rho v. So I just want to write it in this form, whatever form I have over here. So if I just write it like this, so let's say common from here, and you will have, okay, sorry. So if I take rho v common from here, and you will have v square by 2 term plus epsilon by rho plus p by rho. So, yeah. Okay. Okay. So yeah. So if I write it in this term, now this thing is what is called the H. Okay. Now what is the physical significance? Now epsilon, as I said, is the internal energy. Rho v square by 2 is the kinetic energy term. So this becomes the total energy. So the change in the total energy is equal to the flux of the total energy. So if you have seen that the flux of any term is represented by V times that term. So again, so if you see this is the kinetic energy term, this is the internal energy normalized by density, plus there is a pressure term also, right? Which is also contributing to the flux of energy through that volume. right? So this thing in together, like the internal energy plus the pressure together, is called the enthalpy, which is denoted by H, right? So this whole thing is the flux of energy that is going out through that volume, and that is contributing to the change in the total energy. Okay. So if you see here, there is an additional pressure term which is also leading to the change in total energy. Okay, any questions on this? Okay. So then, this is the last topic for today. Uh, After that, if we get time, we can do one or two problems. Okay, but okay. So now we will study three terminologies that are necessary for this. So one is streamline, another is streakline, streakline, another is pathline. Okay. So what does these three mean actually? So I'll just explain first physically, and then we'll go into the equations. So for example, let's say if you trace a particle. So in this figure, so this is just taken from Wikipedia. So if you just trace a particle, uh, you know, so for example, this red line. So this red line shows how the particle moves in this fluid, right? So if you just follow the particle, you will trace out this red line. So this is called the path line. Okay, that's simple. You just follow the particle, and you that is the locus of all the points that the particle has moved through. Now this blue line is uh, is something called the streak line. So what it means is that it will follow the particle, but it will not be just the particle path. So for example, if you you know put a die, if you die some small particle, right, and you just put the particle inside the fluid, right, and then whatever the path that die moves through the velocity field, so that will be traced out by this blue line, which is called the streak line. Okay. So the die will follow the particle because it is associated with the particle, but at the same time, it will move under the influence of the velocity field. So it will not be exactly the particle path, right? The particle path could be turbulent, but the die would follow you know, the velocity field that it encounters. Uh, on the other hand, the streamline, which is actually the mostly used concept out of the three things. So that is basically uh, so okay. So if you consider every point in the fluid, every point that the particle moves through, okay, and if you construct a tangent of the velocity field, right, at that particular point, then what you will get is this streamline. So the streamlines are these, dotted lines which are moving uh, in the fluid. So these are the instantaneous tangents at every point that the particle is moving through, right? So these are basically tangent lines. Okay. So the mathematical definition of a streamline is V dot dl, V cross dl is equals to 0, right? So because it is tangent to the velocity field, right? So that's why the cross product should be 0, right? Because as I said, if you have uh, two vectors in the same direction, their cross product would be 0. Okay? So that's the definition of a streamline. And okay, so now another important thing that we can have from here is something called the Bernoulli's theorem. Now, okay, so let's see this equation, right? So if you remember the Euler's equation from here, so if we consider steady state, again, this del V del T term will become 0. right? And you are left with, as I said, we have decomposed this v dot del v term into this term, del of v square by 2 minus v cross omega, right? And this equation will reduce down to this equation, okay? In steady flow, under steady flow conditions, right? Okay. Now, what you will do is again, gather the terms with gradient together, right? And basically do a dot TL of those terms. Okay. So let me again go back to the notebook. Maybe we can do it here. So let's see this equation. Let's start with this equation. So we have del v square by 2 minus v cross omega equals to minus del p by rho. I hope I got the signs right. Okay. Yeah. So yeah. Now what we'll do is the whole equation will dot it with DL. Right? So del of v square by 2 dot DL minus v cross omega dot DL minus del p by rho dot DL minus del phi dot DL. So yeah. So okay. Now let's look at this term v cross omega dl. So there is a identity which states that a cross b dot c equals to c dot b sorry c dot a cross b. Okay. So if we use this will reduce down to dl cross v dot omega. Now what do we know about for streamline? For streamlines, this becomes 0. dl cross v is 0, right? So if we calculate the whole thing on a streamline, then what it will say is that del of v square by 2 plus phi plus p by rho dot dl equals to 0. So it just states that this quantity is constant on a streamline, right? So that's what the Bernoulli theorem says. Okay. So, okay. Now quickly, okay. So now we know. So another concept that we will study is that of a stream function. Okay. So for example, for an incompressible fluid, we know that del dot V is 0, right? We also know that divergence of curl is basically 0, right? So if we can express this V velocity in terms of some vector potential, so such that V is curl of that vector potential, so then this condition is automatically satisfied. Now note that you can only do this for an incompressible fluid. So whenever a fluid is incompressible, you can always express V in terms of a vector function, curl of a vector function, and this vector function is called the stream function. Okay. Now, if you are familiar with vector calculus, you know that if you have a fluid which is in only two directions, 2D flow, that is, you have x component of velocity and y component of velocity, then this vector will turn out to be a vector in the z direction. It's a function of x and y. So this psi is called the stream function. And if you just expand this equation, if you just take curl of psi, so you'll get Vx equals to minus del psi del y and Vy equals to del psi del x. Right? Okay. So yeah. Okay. So so we have some time over here. So let's do some problems based on some of the concepts that we covered. Okay, so let's say that you have a velocity field. So by velocity field, I mean, let's say you have given the velocity function to be something like this. Minus y square I cap minus 6x j cap. Okay, so this is a velocity field. Now, how do you calculate the streamline? Okay. So the equation of streamline is del x del L cross V equals to 0. So this can be reduced to a simple form del x by Vx equals to del y by Vy equals to del z by Vy. So here it's only a 2D flow. So we don't need this thing del z by Vz. So we can calculate the streamline just from this equation. Del x by Vx equals to del y by Vy. Now, your Vx is minus y square, Vy is minus 6x. So we just put it over here, del x by minus y square equals to del y by minus 6x. Therefore, minus 6x dx equals to minus y square dy. Okay. Yeah. And then you just integrate it plus with some integration constant c. So this will be x square by 2. So minus 3x square. And this will be minus y cubed by 3 plus c. So this is your equation of streamline, right? Now, if you are told that what should be the equation of a streamline passing through a given point, let's say passing through this point 1 comma 1. So then you just put the values of x and y over here as 1 and 1. So minus 3 equals to minus 1 by 3 plus c. And then you can get the value of c, which is minus 3 plus 1 by 3 minus 8 by 3. Okay. So then you can get the value of this constant, and this is the equation of your streamline. Minus 3x square equals to minus y cubed by 3 minus 8 by 3. That is just okay. So this is how you find the equations of streamline. So this is an easy example. Okay. Uh, let's do another example on circulation. Okay. So let's C. Okay. So widely known concept in fluid mechanics, irrotational vortex. So what does it mean? So it means that your flow function, your velocity u theta is basically some constant c by r, right? So it is used very widely in many physical cases. So for example, one physical case you can see that uh, let's say you have some cylinder, okay, and uh, for example, in case of a turbine, okay, and you have some fluid or water around this, and you are rotating this cylinder, okay, such that the fluid around it also gets dragged with it, with the cylinder. But you're rotating this inside cylinder, okay, and as you go further and further out, the velocity of the fluid will keep on decreasing, will rotate with a much faster velocity compared to fluid which is outside. So this can be visualized with uh, function which is u theta equals to c by r. Okay. Now the question is calculate gamma for this kind of uh, flow velocity, right? So yeah. So basically, how do you do that? Also try to calculate omega, which is the vorticity. Okay. So gamma, as we know, is omega dot ds, also given velocity. Okay, so given velocity, we can also do a circular integral of velocity p dot dl. Okay. So now, okay. So now you are given the theta component. So this is not the xyz. We are working in polar component, polar coordinates r theta. Okay. So for theta component, you know that dl in the r direction. So dl is given by dr r hat plus r d theta theta hat. Okay. I guess you all know that. So if we use the second formula, so gamma is basically integration over v dot. So here you have only the theta component, u theta dot r d theta, right? So this is theta hat. So theta dot theta is 1. So u theta times r d theta. And the integration limits would be 0 to 2 pi. This will be a closed integral, okay? Between 0 to 2 pi. So u theta is c by r. So you get a 0 to 2 pi integration c by r times r d theta. R will cancel. So you have c d theta. And this will be 2 pi c. Okay. Now, what will be the vorticity? Omega. Omega equals to del cross V. right? And curl in polar coordinates is given by 1 by r del r of r u theta minus 1 by r del u r del theta. Okay. So if you just put the value over here, so u theta will basically be, so if you just replace this with c by r, so r will cancel, and again ur is already 0, so no need to bother about that. So r will cancel and you will get del r of some constant c, which will become 0. Okay. So this is an example where you should try to see what is happening. So even if the vorticity is 0, the circulation is not a 0, not vanishing, right? In fact, the circulation is constant, right? And where did we calculate the circulation? So we calculated the circulation over, so yeah, over any closed loop around the center. So if this is the center, for any closed loop, this circulation is constant, no matter what is the distance of the loop, right? So at R1, whatever circulation you have, at R2 also, you have the same circulation, gamma, right? Because the circulation is constant and not a function of R. It doesn't change with R. So this is a case where even if vorticity is 0, circulation is non-zero. Okay, another problem that was given in, you know, uh, that was asked as a homework question in the lecture. So we'll just do that and end the call. So any questions up to this? Okay. So if you have seen the lecture carefully, so in the conservation form lecture, so the professor has asked if you can derive a similar conservation uh, theorem or a conservative form of v dot omega. So conservative form of v dot omega. So how do we get a conservative form of v dot omega? So remember what we mean by a conservative form. So del A del T should be equals to del dot something, right? Some flux. So can we have a form uh, like this for this quantity v dot omega? And why this is important? Because this is something called helicity. V dot omega dv. This is a physical quantity called helicity. So we'll go into the physical meaning of it later on. But let's see if we can derive a similar form for this quantity like this. So what we do is we are doing del H del T. Okay. So integral over del T of v dot omega dv. Right. So let's first write del T of v dot omega using chain rule. We have del v del T dot omega plus v dot del omega del T. Okay. Now from Euler's equation, Okay, so these are all del, okay, partial derivatives. So from Euler's equation, we know what is del V del T, and also we know what is del omega del T from the vorticity equation. Right? So we can write this as V dot del V minus del P dot rho, this is minus dot omega, this is the first term. Second term is V dot omega dot del V minus V dot del omega. So if you remember, so del omega del T from Euler's equation, sorry, from vorticity equation, del omega del T was del cross V cross omega. Right? So if you break this term, so this will reduce down to omega dot del. So there is a vector identity. Maybe you can look it up later on, but if you just Google it, you will get this identity. Del cross V cross omega is equal to this. So actually, there are few more terms which includes uh, V times del dot omega plus omega times del dot V. But these two terms will become zero, right? These two terms will become zero because this is incompressible, and del dot omega will become zero because omega is curl of V. So divergence of a curl is zero. So that's why these two terms will become zero, and this will reduce down to this. Okay, so there is should be one minus sign somewhere. I don't remember the identity, but one of these will be minus. Okay, you can check it on later on, but anyway, these terms will become zero. So okay, so that's why this will reduce to this. Okay. Now, if we just look at it quickly, okay. Del P by rho dot omega. Okay, so let's expand this term P dot del P dot omega. So this first term. Okay? So let's expand this first term. So we have Vj omega I del Vi del xj. So when you have V dot del, so these in indices, this index Vj and xj would be same, and the rest is then you have del of V dot omega. So these two index would be same. So II and Jj. Okay. So this is how you expand this term. And the other term is, so this is the first, second. So let's say the third term. So this is the first term, this is the third term. So if we expand the third term, that will become V dot omega dot del V. So here there is a omega dot del. So that means omega and del index will be same. Vi omega j del and the xj of Vi, right? So if you just do a quick manipulation, you can just interchanging I to j, okay? And Vj, yeah. So that's it. So okay, these two terms should cancel, but I am saying that there's a index. Okay. Yeah, I think let me write it down. Okay. So I think there is a okay. There is a property which says that a symmetric tensor multiplied with an antisymmetric tensor will become zero, right? So if you see the first tensor Vj omega I is an antisymmetric tensor, whereas this one is a symmetric tensor. So that's why I can interchange the indices j to I and I to j. So yeah, just look it up and basically why this interchange is possible. But if this interchange is crucial to for the cancellation of these two terms. So basically, one and three terms, the first and third term will cancel with each other. Okay? And then if that happens, then we are left with uh, so then del t of v dot omega is equals to minus del p by rho dot omega minus p dot v dot del omega. Okay. So we're left with only the second and the fourth term. Now for the first term, I mean the first term in this equation, so that is if we consider this term, we can take the omega uh, inside the we can write it like this. Why? Because del dot omega is zero because omega is a curl. So divergence of a curl is zero. So we can now there is another identity which states that this is equals to uh, del dot v v dot omega. So this just look it up how this goes from here to here. Maybe I will post the notes in detail of how this goes. But the main idea is that uh, finally you can express this helicity. So del v dot omega, which is helicity, in a form which is del dot p by rho omega plus v dot omega. Okay. So this is the conservative form, this for v dot omega, which is the helicity. Right? Well, there is a minus. Okay, so I guess we're out of time. But if you have any questions, let me know. So for references, yeah, sure. Yeah, go ahead. Right. So we combine. Yes. So you can also have an integral form, or you can also leave it like this. So if you have you can have an integration on both sides as well over dv, or you can leave it in this form as well. Well, to be honest, so this is not h actually. This should be p dot omega only, right? Because h is only if you integrate over volume. Okay. So maybe the confusion is because we started with an integral form and then we converted it into a different this equation, right? So I think everything follows from there, right? There is no integration involved over here. Is that clear? Right. So now to get helicity, you will just integrate both sides volume. So then you will get b dot omega dv. So then it will become dh dt. And if you integrate this, you can apply the divergence law, and then this will be integral of this thing over the surface. Okay. So that's why we try to conservative form, right? Because we can easily have this thing. So anything in conservative form, del A del T plus del dot flux equals to 0. So you can always integrate it. So del T of A dt plus, sorry, A dv plus del dot flux dv equals to 0. And this flux you can, instead of doing a volume integration, you can integrate over the surface. And yeah, you can check what is the change in the quantity in that volume. So this both integral and the differential forms are interchangeable, right? So it doesn't matter which form you have, but you can interchange them between each other. Any other questions? Okay, so for reference, so for particularly for week 1 and 2, I would say that this book is very helpful, and particularly chapter 3, 4, and 5. You don't have to go through the whole book. So, chapter 3, 4, and 5, uh, you can go through. That covers the whole material for week. Uh, okay. This Carson Huang, statistical mechanics. Week 3, and even I think this fluid mechanics book by Kundu and Cohen. So this is going to be very helpful for you. So they start with a very basic approach. So even if you don't know um, even if you don't know vector calculus, right? So they start with vector calculus, like what does this del dot and del cross, these terms, where do they come from, and everything. It is a very fundamental to advanced approach that they take. And as we go forward, I will also give other references of books on fluid. But till now, till week 3, I think these two books cover it all.